I'm Nathan Mankiewicz, and today I'll be talking about chordal flag averaging and its applications. This is joint work with Tolga Birdal. So the first question you might ask is, what is a flag? Well, it's not, these are all flags, but the flags we're going to be talking about are not quite these. This is a flag. It's a sequence of nested subspaces of a vector space. So the idea here is this purple thing in the middle here is a line inside a plane living inside n-dimensional space. The line and plane pass through the origin, of course, represented by this black point. So we have two flags here on the left side, a red flag and a blue flag, a line inside a plane inside n space and a line inside a plane inside n space. And we average them with respect to the chordal distance on the manifold, which gives us this purple line inside plane inside n space. So there's some properties of these things. Flags generalize other spaces like Gauss-Monnians. They have a nested structure, and we found that they're actually robust in our experiments. So why do we say chordal flag mean and chordal flag averaging? Chordal flag mean for averaging with respect to the chordal distance on the flag manifold. So how do flags represent data from computer vision? For example, video clips. Let's say we have a few video clips or a few frames from a video clip. In this case, a very short one, 3 frames. We start out with a collection of images on the left-hand side, then we vectorize and stack them, then we do the QRD composition, then we take the first 3 columns of Q as basis vectors for these subspaces. Now the question is, how do we generate the nested subspaces out of these basis vectors? And these give us flag representations for this video or collection of images. So one way to do it is to take the first basis vector inside the span of the first and second, inside the span of the first, second, and third. Or we can do a number of other combinations. In general, flags generalize subspaces by maintaining the order or partial order of the frames or the vectors, the basis vectors in these subspaces. So in this work, we did averages on the flag manifold with respect to the chordal distance. The flag manifold, by the way, is the collection of all flags of the same signature. The signature of the flag is just the dimension of this nested subspaces, the dimensions of each of the nested subspaces. So our problem was averaging a collection of flags by computing the chordal flag mean and flag median. And we came up with 2 algorithms, one for the flag mean, which essentially involves translating this problem to the Stiefel manifold, and the second one, which is the flag median, which again translates to the Stiefel manifold, and then does iteratively reweighted chordal flag means. So a couple examples of this were flaggy faces. So I don't know if you're familiar with the classical eigenface problem using the SVD. In this case now, we're sort of using our flag manifold averaging method to average a collection of faces. The idea here is that each row is represented by one flag, and then we average them into the upper image, which is the average on the flag, and the lower image, which is the average representing each collection of images as a subspace. And we notice that our flag type 1, 3, so a 1-dimensional subspace in 3 space in D-dimensional space, maintains the center illumination. So we're able to prioritize the center illumination in a way that can't be prioritized by subspace averaging. Another example is averaging motions represented as flags. And the idea here is that we are able to use our flag averaging methods to average motions, and we're able to get averages which are robust to noise and robust to outliers. These are the yellow and the blue, the purple points, and they're lower than standard motion averaging methods. So we had a number of contributions. I won't list all of them. For more information, please see our paper. Thank you so much. I would like to acknowledge Benjamin Busum for introducing Tolga to me. And also I'd like to thank Yajing Liu for her helpful talks, translating this problem to the Stiefel manifold. Thank you.